Today, this video will cover the part 2 of our discussion for chapter 10, which covers complex annuities. Now, in the last video, we discussed on how to solve complex ordinary annuities and complex annuity dues when your C, or your number of compounding periods per payment, or per period of payment is greater than 1. Now remember that your C can be solved by, for example, if the, what do you call this one? If your payment is made quarterly and your interest compounding is made monthly, then your C would be the number of compounding periods contained within a payment period. Now, your payment period is 1 quarter. So it's quarterly. So 1 quarter is equal to 3 months, and your interest compounding is monthly. So meaning your C would be 3 because there are 3 months in 1 quarter, meaning there are 3 interest compounding periods per one payment period. Now, when C is less than 1, or in cases wherein you make your payment monthly, but your interest is compounded quarterly, then in your payment period is 1, while your interest compounding your payment period is 1, while your interest compounding is 3. So that would become 1/3, which is less than 1. I'll show you an illustration to you later on as we go through. So now, before I continue, let me turn off muna my camera para dili mag-agaw ang ato ang signal. Okay. So before we continue, this is actually the discussion for part 1. And let's add a sheet here for our part 2. And let's just copy muna our formulas for fair value of ordinary complex annuity, present value of ordinary complex annuity, fair value is future value, future value of complex annuity due, and lastly, we have our present value of complex annuity due. Okay, so our final formula for ordinary complex annuity, the future value is this one. This is for our reference book, and this is based on how I solve it. And then the second one, we have for our PVOCA, so we have this one. And on how I solve it, we are going to use this one. Next is our VCAD, or fair value of complex annuity due. This is the formula for that. But also I solve it using this one. And then, so for PVOCA, a reference book taught you to use this formula, while I am used to using this formula. Okay, now let's go to our problem. So first, we'll concentrate muna on our what do you call this one? Ordinary annuities. So we start here. Okay, but we edit this to make it to change it into wherein C is less than 1. So payable at the end of each month for 10 years if the interest rate is 6% compounded quarterly. So here, the payment is still the same. Payment is 100. What else do we need? Our INOM is 6%, making our I That would be 6% divided by quarterly, so 4. Okay. Next is our N, which is our number of payments throughout the term of the loan. So that's, we have time of the loan, which is 10 years, and we do it monthly, so that's times 12. And our C here is our uh, number of compounding periods per number of compounding periods per payment, your period of payment. Okay. So now guys, for letter C kasi, I think I failed to show you last time how you would solve C. So the formula for C is actually um uh let's just say number of months. Kaya medyo ano siya, kanang, or if you would prefer number of days, pero let's just stay muna here sa number of months per payment period, and then you divide it by the number of months per compounding period. So if we use this formula, guys, remember here on our first example, so here, right, so if we would use this formula, no, for our C, now our number of months per payment period is 3, and we divide that with the number of months per compounding period, which is 1, you'll get 3. So that's for your C. Para you'll get a better idea on how to solve C. Now here, sa ato ang C, where C is less than 1, and nakayunta, no? Well, the number of months per payment period is 1 month, while the number of months per compounding period is 3 months, because 1 quarter is equal to 3 months. That's why our C here is 1/3. Okay? Or 0.33333. Okay? So now our C here, our NC now becomes n times C, so that's 120, multiply that by 1/3. So our NC here is 40. So with that in mind, let's solve our FVOCA by substituting our values here. Our payment is 100 pesos. Our I is 0.015. Our NC here is 40. And on the lower part, again, our I is 0.015, while our C is design fraction, 1/3. One, okay. So if you input this in your calculators, so I'm just gonna use my calculator, okay? So that's 100 times 1 plus 0.015 raised to the power of 40 plus 1 over 1 plus 0.015 raised to the power of 1 over 3, and then you deduct 1. So you'll get 16,361.50. I hope that you got the same answer with me, okay? And I hope that while viewing this video, you'll do your solving with me as well. Okay, so for on my part naman, on my side of the coin, before I can proceed with our old formula for future value of ordinary annuity, I still have to solve for our IE. Now, again, for our IE, um, we have to know first the effective annual interest rate of the compounded quarterly. So for our compounded quarterly, that's one. Okay, let me just insert formula. Boss. Why can't I insert equation? Okay, equation. Okay. So for our, this is for solving our IE. Let me just copy it here. Let me just copy this first. For our IE, For our IE, so our formula for our IE is it's 1 plus I raised to the power of, oh, I forgot this again, design. Again, it's 1 plus I raised to the power of m, and then we deduct 1. Okay, now since our IE, let's just say this is our IE sub 1, IE1, and then we equate this to our, and then for IE2, formula will be the same. And then we equate our two IEs. Okay, so for our IE1, we know that this your IE1 will pertain to the interest compound, original interest compounding, or our original compounding periods. And then we equate it to our, we equate it to, this should be equal to, okay, happening. Okay, we equate this to our, what they call this one, our, from our original compounding period, we equate this to the payment period. So in this case, we are trying to solve here, down, down. Okay, so we're trying to transform our compounding period, which is quarterly, into monthly. Okay, so first is our quarterly payments, a quarterly compounding period. So that's our I here is 0.015, and then our M here, since this is quarterly, because our interest compounding period is quarterly, is 4. So minus 1, we will get here how much? So that's 1 plus 0.015. We raise that to, we raise that to 4, and then we deduct 1. Okay, so this is our IE now, our IE1, and then our IE2 is so this is 1 plus, our I is unknown, but our M is, we know our M, which is monthly, so 12 minus 1. Now, we substitute here, since we know that IE1 is equal to IE2, so we can substitute IE2 here with 0.06 1364. Okay. Now, it would be very useful on your part to use the store function instead. So, on my part, I'll be doing muna the first part, the 1 plus 0.015 raised to the power of 4 less 1 on my calculator. And then I will press now Shift, the store button, and then to A. So I have stored my value of 0.61364 on my A button, and then from here on out we will now simplify this formula. So let's just so let your 1 here, your minus 1 here, will be transferred to the other side. So what will happen now is you will get, let me just transfer here on the this one on the other side, because, and this one too. Let me transfer this to the other side. Oh, chosen. Good in this. On the whole expression. Oh God. Just bear with me on this, guys. Okay, there we go. So this one will the chan will know like that. Oh my god, it just ruined everything. And yeah, let me just copy this again. And sir, what happened there? Why did it become 1.061264? Now remember that we transferred our -1 to the other side, so it now becomes 1 plus 0.06, thus the 1.061264 in a function. Okay, now our missing item here is our I. So for us to get our I, we have to transfer our to the power of 12 to the other side, so it will now become square root of a 12th root of this one, and then we transfer our plus 1 to the other side, so that's -1. So it would look like this. So then we erase this. Okay, I is equal to design. Let me use my cursor first. Radical sign, this one. Okay, so let's get, so this is our 12th root, and then we copy this one inside. Yeah, and then we go outside and we deduct one from it. Okay, so again, this this expression became like this because we transferred our to the power of 12 to the other side, so now it becomes the square 12th root instead of the power of 12, and then instead of positive 1 here, we transferred the 1 to the other side, so now it becomes -1. So if you would solve it, if you would solve this in your calculators, our I now, or our equivalent, or our IE now becomes, so our IE now becomes, so this is 12 through to 12 of, again, I used my what we call this, my store function, so that would be 1 plus alpha A for me, and then I deduct 1. So now I would use my store function again. So I would press shift store Bravo. Okay, that's on my Bravo side now, and I actually got can I don't know how to yeah, okay, so I can do that. Okay, so 1 plus this one, and then I raised that to fractional form, so that's 1 over 12. 1 over 12 actually, an exponent of 1 over 12, guys, actually can also be expressed as a radical sign, okay? In case you don't know that, and then -1. Okay, so you should have gotten this. And it would be better for you to use your store function. So I stored this information on my calculator to my B button. So this is how I solved for my equivalent I, and now I can move forward with this formula. Okay. So again, right now it may seem so. It may seem that my way is longer. I know it is. It's just that this is more comfortable for me, and you may use my way or our reference book's way, whichever suits your boot. Basta on my part lang is yeah, more hiyang when I'm using this one. So this 0.004975. 3 to the power. Our n here is 120. 1, and then okay, that's 0.004975. So if I would solve it here, hopefully I will also get the same answer as I did while using the formula for while using the formula as indicated in our reference book. Okay, so we raised that to the power of 120, and then we deduct 1, and then we divide this by this one again. Okay, so as you can see, guys, they still arrived at the same answer. Okay, so let's move on to the present value. So what if it's the present value? Okay, so if it's the present value, then let's copy this and paste it here, or we can just use this. No, yeah, we can use this. Oh, no, not that one. Okay, and then we transform it to PV, OCA. No, not that one again. And then, so this becomes one less, and this will disappear. Oh, this will become negative, and this will disappear. Okay, so if you input that on your calculators, you should get what is that? 100 times 1 less 1.015 raised to the power of negative 40 over 1 plus 0.015 raised to the power of 1 over 3, and then you deduct 1. Okay, so you should get 9,009. Can I think I can actually, I just wrote that down. Okay, sige. 9,019.48. Okay. So now let's try my way. So I get the same answer as well. So I'll just copy it here and place it here. Make this a PVOCA, and then I think for here, and this becomes one less, and this becomes negative. Okay. So with that, let's see. I hope that I will arrive at the same answer as well. So this becomes 1 plus this one raised to the power of negative 120. But before that, now I'm going to share one less here. And then this will disappear. And then for this one, this will be transferred here. Okay. So again, we still arrived at the same answer. Okay. Now, um, now let's go to when it's an annuity due. Okay. So let's use another set of question, like what we did during our discussion on the first part. So if the interest rate is 6%, this becomes compounded quarterly. What is the future environmental value of an annuity of 150 payable at the beginning of each? Oh, what happened here? Quarterly at a month for 1 year. Okay, so again, what do you call this? Our payment here is 150, and our now let me just do that. Okay. Our payment here is 150. Our INOM is 6%, while our I is equal to 6% divided by 4 because it's quarterly. Okay. What else? What else? What else? What else? Our N here, or our number of, what was our N here? Let me just copy and paste this. Our number of total payments throughout the term of the loan. So that's our term of the loan is 1 year, and our payment is made at the beginning of each month. So that's 12. While our C again is the number of months per payment period. And then, so our number of months per payment period is 1. And then we divide that by our number of months per component period, which is 3. So 0.33. Now our NC is equal to, that would be 12 times 1 over 3. You have 4. Okay. Now, as you can see, guys, um, this problem actually has, let me just this. Okay. As you can see, guys, oh, this problem has the same, what do you call that? C with our has the same C with our ordinary annuity. So with that, our solution for our equivalent interest rate per compounding period will be the same. But before I copy that, let me just move this muna further down. Okay, and then I'll copy this again. I guess we could just put it this, anyhow. Okay, so with this, let's proceed to solving our um, future value of complex annuity due. So our payment here again is 150. So we have 150, and then our I here is 0.015. Our NC here is 40. All right. Oh, no, it's not 40. Our NC here is 4. It's only 4. I'm sorry. And here again, it's 0.015. And our C here is a fraction. It's negative 1/3. Okay. So with that, if you enter this in your calculators, this would be 150 times 1.1 plus 0.015 is the power of 4 less 1 over 1 less 1 plus 0.015 raised to the power of negative 1/3. Okay, so you should get 1,859.29. Okay, while if you would use my formula, what would happen here? Why did they copy the same formula for me? Okay, again. That one. This should have been the one that I copied from FCAD. Let me just paste it here and then erase this one. Oh no. Okay. Okay. So while if you would use my formula or my way of solving, so our payment here should be 150. Our IE is, what's our IE? It's 0.004975. Yeah. Our N is 4, no, 12. Sorry. N is 12. And then again, 0.004975 plus 0.004975. Okay, so if we input that here, actually, yeah, okay, let's just do it here. 150 equals 150, and we multiply that by 1 plus our equivalent na interest rate per period, and we raise that to 12. Then we deduct 1, and then close it, and then over 0.004. No, this one again, and then we multiply the whole thing with 1 plus then this one. Okay, what happened here? Oh, okay. Why did I do that? Okay. So again, either you use the way of our author or my way, we'll still arrive the same answer. Now, lastly, let's go to our present value. So let's just copy this one for easier, for fast, for expediency of the process. Okay, we got, so this one will be, now it becomes 1 less. So if we solve this on our calculators, so that's 1 less, and this should be negative 4. Okay, solving now. Oh, no, 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 no. Okay, so we should get 1751.79. While on my way of solving things, let's check if we can arrive at the same answer. So this is EVCAT. This is now 1 less, and then this is negative 12. Okay, we delete the no minus 1. Okay, and then let's see if we arrive at the same answer. So that's 150, and then we transfer the 1 minus here, and then we raise this to negative 12. This is your score function. And then again, your store function, which is on my calculator is alpha b. And then last one, store function again. So whether you use our reference book's way or my way, we will still arrive at the same answer. Okay. So with that, guys, this ends our discussion on our what do you call this one? This ends our discussion on ordinary annuity and annuity due, complex ordinary annuity and ordinary complex annuities and complex annuity dues. And I hope that you have learned something. See you in the last part of this series. Um, there I'll be discussing the remaining topic for chapter 10, which is deferred complex annuity, and then the deferred perpetuities. So um, uh, again, I hope that you have learned something, and I hope to see you on the last part of the video of the series. Thank you.